hold on. Can you see me? Am I up on your screen? Do you have the witnessnesses? Do you have me? Hold on, I think we can click something, do something. Let's make this change. Let's see if we can get realigned everywhere and everywhere that we might be. That's right, right now you're just waiting, and I'm waiting for everything to align perfectly so we can all do this together in harmony. Right, we're waiting for all the servers to line up. You can hear me say, welcome to the show. It's me, 3D, with 3D Change Perspectives. And today, I want to change your perspective on, well, it's a little bit convoluted, but basically what already exists. Procedures and things that are already there. I kind of want to show you a different way to look at them, and we're going to use maths, numbers, and some generic sharing protocols to kind of help explain my point. So, being just before the new year, I felt it might be more fun to do a math episode instead of what we normally do. And don't worry, I have a way to help also to use your YouTube clips or channel as maybe website ads or some other kind of ad sponsor role thing to help you out with your channel. But I do want to start off with better generic trustless sharing protocol. And then work my way through the numbers to get to the main YouTube bit. So right now what I'm doing, so you're perfectly aware, is we're getting the chat set up on YouTube. So basically no matter where you're watching this at, you could be on a bunch of different places watching me, listening to me right now. But if you jump over to YouTube, you can actually join into the conversation up on screen. We don't actually get a whole lot of people that show up all that often, and that's fine. When we do get them, we're always welcome to see them. So before we keep on going, I need to jump into sponsors. I want to thank, first off, our network partnership. Thank you, DeOrganized, for being one of the most recent Bitcoin Live digital broadcasting DB partnerships. Bitcoin Live DB and DeOrganized is a powerhouse combo. We are growing, and this is a beauty to see, especially with some great people like DeOrganized, the company. Now, I also want to thank our actual network sponsor and sponsor today's episode. If you go ahead and look over on the corner down there, there should be a little QR with an S. That is the Shield Folio S, of course, and that means that if you scan that, sorry, I'm reading and doing something else sometimes. If you scan that, you'll actually be able to go to their website, and if you go to their website, you'll be able to see more from them. And we're actually going to be talking about this Shield Folio specifically, which you can see the thing behind me. We also got the same QR there. It is a little black book. That's exactly what it is, a little black book. It's made with stone paper, so it is tear resistant, fade resistant, all sorts of different resistances in order to help basically make it's just basically to make it easier for you to store your private keys, your wallet keys, well, not your wallet keys, your website keys, your passwords, addresses, all these different little things. And because, like I said, it's tear-resistant paper. And when you have tear-resistant paper, this basically allows you to do a little bit more. And when I say do a little more, I mean like it survives and goes through without having to be completely worried about being destroyed like regular paper. And it being a little black book, it's easier to hide, conceal, move, and carry with you. Alrighty then, now if we got everything set up, you're gonna see hearts popping up, and that's awesome. Alright, so jump over and use if you use the code BitcoinLive20, you get 20% off your portfolio today. And let's go ahead and jump into the jump in before I lose my words more. Oh yeah, thank you again, Shieldfolio, for sponsoring today's episode in the network. Hopefully I can get this set up one of these days where I'm a little bit easier on the words. But today I'm a little bit frazzled. It's been a heck of a setup. I've been working frantically to get today's presentations set up and ready. And to be honest, I guess it's a little bit of labor of love, so to speak. But I think today's episode is gonna be really fun. Like I said, it's a little bit different than usual. Normally we're going after one specific topic or whatever, and today we're just going to show you some processes, and then we're going to show you a completely new way to do basically all three of these processes. All right, well, let's get started with what we are talking about. We are talking, first off, we are going to hide this, and as we go throughout the day, you're going to see this little pop up. If you see that QR, that means you can scan it and show up to where I'm at now, which means you can follow along rather with me right now, or in the future if you're watching later on. It just basically allows you to access it anytime. There's also, if you're on YouTube, in the description, there should be the links later on, added in after the live stream. So here is, it's a video by Stand Up Maths, by Matt Parker. So it's 18 mathematicians break my secret Santa method is what the name of it is. And it really is exactly what it sounds like. On this episode of Stand Up Maths, they go over a methodology for doing a trustless Secret Santa. And in this episode, when this episode first popped off, I didn't think it would have as much impact on me as it did. Like, when I first saw that, I'm like, oh, I'm not big into Christmas. But it ended up catching me in big ways. It really sparked some motivation because I was already working on something that not similar, but they have really nothing to do with each other. But I'm attacking both things in the similar method. Or at least the demonstrations are being done in the similar method. So, and again, this sparked a 48-hour learning adventure, and we're going to recap just a little bit of that with you to now. So, first off, I have heard before about Trustless Secret Santa, and I don't think I had really heard anybody say those words in like half a decade or more. So somewhere between 5 and 10 years, and as you can see, there's even like in Security Stack Exchange, Secret Santa implication that does not require a third party or central authority, and it's a real thing. It's something that blockchain technically has been trying to solve. There's been tons of like torrents have different trustless ways of doing stuff and whatnot, and even getting now more to a quantum trustless is on its way. So with this being a real conundrum on how to do what is actually a very exploitable process, first you'd probably be able to guess that foul play is just the #1 problem with a trustless sharing anything, because someone can just do whatever they want. They can move to a location, or they can just choose not to follow the rules. So let's see first what problems Matt faced before we can continue to assume loopholes. You know, it's best to see what someone else has discovered or figured out before we try to rediscover or figure that out. Well, actually, you know what? I just realized I did not give you a link for the pre-search. If you did actually want this pre-search search, so you can actually see this one. Here you go. Now let's go back over. Here we are. So I have a little clip to make it easier to find this exact thing. So we're just going to let him play.
At the very end, once the shunt has happened, and we're passing around those numbers for people to see who they're buying for, because when one person gets the list, they know that everyone after them in the cycle, which is public, hasn't seen it yet, and the people before them will never see it again. There's room for some shenanigans, as Tom7 correctly noticed.
Okay, so there was one hack that we discovered, which takes place in the last round, and it comes from not complying with the algorithm as written, but in a way that's hard to detect. So as I receive the list, it contains pairs of pseudonymous sender IDs.
Okay, so it looks like something just worked. Yeah, so YouTube broke on my end. Basically, that was the clip. It comes down pretty simple. It's pretty common error, pretty common problem. But I think the best part of this clip is shows that out of 18 different maths people, of course, they figured out, found, and made some loopholes. It's gonna happen, right? We're about to drop off some of these old ones. I'm gonna go to the next one, because I don't think that's gonna play. And trust me, I had all this stuff loaded before we got started, and now it's all acting like nothing is loaded. So let's, oh, of course, yep. Alright, so this is the second hack, so to speak. And I think this is probably the number one problem with trustless protocols in general. We ain't gonna try expanding it because that just bring it to play. If we get to play, I'll turn off the mic and let it play so you can hear what they have to say. Because it's just a very basic generic.
I hacked your Secret Santa protocol. This is the thing. I chose who to buy for. I feel quite bad about it because we had you sent the protocol in advance, and I didn't have a chance to look at it. And then round one came, and I still hadn't looked at it, and I didn't really understand. I just thought, well, I need to put two numbers and pass it, shuffle it, pass it on. Fine, did that. And then it was when I was waiting for round two that I got to thinking, what is it that I'm going to get back, and what's that going to look like? The thing is, when I get it back, it's got some names in it already.
Yes.
So I could swap myself to give to any of those people, and then whoever was giving to them, I can swap to give to whoever I was supposed to give for originally. The problem with that is that those might be the same person.
Here's a mock version I've made of what the list would look like when Peter saw it, and they can see their two random numbers they put in last cycle. But let's say they want to take themselves out of the cycle. They realized,
I hacked your Secret Santa protocol. This is the thing.
Oh, okay. So yeah, he realized he could pick and choose who was going to buy from him and who he was going to buy for, because he wasn't at the very beginning and he wasn't at the very end. I don't remember which one we're on the second one, right? Right. So I got two clips for this one. So here he's going to explain it a little. We're going to get a little bit better understanding of exactly what is going on. He actually has a two-part hack, and it's pretty genius.
Now got me giving to me. I can now swap for somebody.
Sorry, everything is reloading. I think normally YouTube that causes this error. It's just crashing. You have the link. You can come back. So basically, he's saying he's going to say because he has it set up now, he is buying for himself. He can now pick who he can swap with someone else, and they can buy for him, or a couple other different things. There is actually a way where he can, at this point, get multiple gifts. So we get something to pump in. Gosh darn.
Now got me giving to me. I can now swap for somebody further up the list and make their gift giver give to me instead, because I know that they're not me.
more than that, because people, on my advice, were putting in their names as their receiver ID, and because the order in which we were emailing this around was public, Peter knew that Sophie was the person directly before him. Which means whoever person 128 here is, they're not Sophie, and they're not Peter, and they haven't yet seen their buying for Sophie. So because Peter knows Sophie quite well, and is like, oh, that'd be a really easy person to buy a gift for, they can take 128, move them down here, so now 128 are buying for them, and put themselves in, meaning Peter has successfully picked the person he's buying for. Exactly what I was trying to avoid.
I can also swap myself to anyone lower on the list.
Anyone after you.
Because they haven't revealed their names yet, nobody knows who they are.
But you don't know how to swap into
I've now got me giving to me. I can now swap for somebody further up the list and make their gift giver give to me instead, because I know that they're not me.
More than that, because people, on my advice, were putting in their names as...
I wanted to replay that beginning again. You guys heard that. He can successfully pick who he's buying for and who is, and at some point he mentions that he's taking a random guess on some of this, but he basically breaks the whole thing. So now I want to show you this a little bit. I kind of want to this is in his video, so I want to give you at least this one last little bit before I give you the context behind it.
their names in at this stage. I originally had them putting in another random number and then later on revealing who they are, and I should have stuck with that, but I changed it because I thought, oh no, it's fine. And I'm trying to get the most efficient version of this system possible. People can put their names in. That did leak extra information that Peter was able to exploit. And so yeah, he was able to choose someone he was going to buy for, which is...
And that's exactly the problem, right? So although Matt did see an extra step missing was needed, he also thinks shunting does something, but really shunting or moving the list, part of the list up and down, like the right side or the left side up and down, and mixing up passing order, so who's the next one to do something. Those are basically the same thing and basically are pointless. So shunting or always changing passing orders are both predeterminable maneuvers that everyone knows about. So even if you said that you have the option to shunt or not, or even if you gave people more shunting options like being able to go up or down, choosing if they can or don't, it doesn't make any difference because it's always going to be predeterminable on what someone did. Even if you don't know exactly who did the shunting, you can just figure out how many people did shunting and which direction they probably went. So because of that, you're never going to be able to. That makes it pointless because it's always going to be predeterminable. That's a pointless maneuver. Shunting and changing the order it's going through people's hands. So to be honest, just force mixing and not allow shunting will actually make up the difference. But I also had an idea to add entropy. Now that brings us to the next point. We're actually going to go into this part right here. So I have a GIST file, or a GIST on the GIST hub for a GTSP, or generic trustless sharing protocol. This is version 2, since Matt has version 1. This is version 2. I'm going to explain exactly how this works, because it's just I think it's under 1,000. Yeah, it's under 1,000 lines of code, 773 lines of code. So I actually made a under 1,000 lines. Yay! Although it's not, I could have easily made it 1,000. We're gonna just jump into a presentation now. This is the presentation I spent a couple days building and getting working. It does everything but the very last step. I'm super happy about that. Here's the actual full-on link to it. Alright, so I tried to get we got a shorter link. It doesn't matter. This one's easier to find. It's right there on GitHub. So we're gonna just give this a try. So, alright, how many parties? I can put in 1, put in 0, and put in any number as long as it's a number. So let's put it in a bigger number. They were using 14, so let's go ahead and use 14. Add 14 people, and then we have a list of 14 zeros. It says click on any 0 on the left side. I'm going to click on a number on the left side. Boom. I have 342 was placed in my slot. As you can see here. Now it says click 1 on the right side. I can click on any of the. Boom. Now we moved it, it's gone around, it's come back to me. And as you can see, every time we put in our two numbers, we then mix the list. No matter what, we mix it up. That's why there were zeros there to start. And everybody takes a zero, and so there are no more zeros, and you always mix the list. So here we can see my first number is 342, my second number is 160, and as you can see here, my 160 is my purchaser ID, and 342 is a receiver ID. And if we look down here, we can actually see I'm the very first screen on both of these. I'm the first screen. And if we look, my numbers, and if we come back, they have been moved. Funny thing, mine is in this other person, because there's two greens, so that's pretty neat. But this will allow us to see our original position. So all the colors is everybody's original positions. I should have probably put the color list up here, the order of that is, but I don't actually remember it. It's like, I just know green is the first one. I think it's like green, gold, purple, red, blue, pinkish, brown, something like that. So I'm going to click the next one to go to the next phase, which is entirely just mixing phase. Everyone's going to mix up the whole list as we go around. You're going to be allowed to move two numbers around on each row. So we did that. So it's a mix full of two sets of times, one set of times for each person. And we're only a couple steps in. Now we need to add in to the third row. So I can click anywhere in here and I add into the third row. Bottom one, cool, I add into the third row. Now we can see all of mine up here, 621, receiver ID 141, my new number, receiver ID, and 12, purchase ID. So the list has also been mixed up already, because I clicked this very bottom one, which is it's green. I'll show you where I clicked. Here's the other green person above me, and if we come to look, my number has been mixed up just right here. One above it, so sure, it's not very far, it's there. Alright, I just realized you guys can't see my mouse, my bad. But anyways, can you see it pop up? Yeah, you can't see it. Cool. So again, you put in a new number, you mix the entire list up as you go. So there are no more zeros. It goes back around, and now you reveal your name in the list. So on these first two sides, on the left, far left, and in the center, are your purchaser IDs. Your receiver IDs, my bad. So you choose to reveal one of those two slots. Your choice which one doesn't matter. And if I look, where's 620? So here's my original first number, 621, is two spots down from where it started. It has moved quite a bit since then, though. My second number has only moved one spot up, but it hasn't moved since it started. And my other one is not, it's completely a different spot than where it started. And all of them are different numbers from when we started. So I can click and I can keep changing these and you see it's going back and forth. So saying, hey, that ain't mine. That one is. Changed and it stayed. So that was my receiver ID right there. If I click on my other receiver ID, it's swapping it back. So cool. Awesome. So just putting in an entirely new row, just simply adding entropy was a huge difference. And when I say it's a huge difference, I really do mean that, because like, yeah, I realize we got this problem into like an equation like if we drop this problem into an equation, it'd be like all your pick positions raised by its own weight added together before then dividing by the result of the exponentially rising of the sum of the total graphical spots raised by the total graphical weight possible. Or, just running this through an MFT, or the modified Futurama theorem equation. So it says here that we do have something else to show. I have a graph and go, yeah. All right, I'm going to kill this web app. All right, so in this graph, I don't have the location for you to find it online. Sorry about that. But you can basically see how the graphing system works. And in the presentation we're just doing, those numbers above that look like number plus number equals number, that was this whole system working out in real time as I was clicking it. So in this, we see four plots plotted on the graph. We can see in red the graph or each spot's identifier or ID, and the top right is that spot. That's how you can actually identify that location. It's the first row. It's on the null. It's the first column, null row. Second column, null row. Third column, null row. First column, first row. Second column, first row. So on, so on, so on. And basically, we take these added position markers, add them together, and then we exponentially raise them by themselves, multiply the loop number. And we then divide that by the total possible, and multiply that again by its total possible, which our total possible loop number is 4. And the graph is 4 by 4, so we have a 4 multiplied by 4. So 4 by 4 by 4 by 4 by 4. Woo! Comes out to a pretty small number. Cool, we're just getting started. The next maneuver we see, and then comes up to 1024. Pretty good. If we go a little bit further, that one comes up to 26 to 144. Much bigger number, and then we get a 1.237 fraction. So as you can see here, if we were to put these together and average them out, that wouldn't be too bad. So let's put them together and weight them out. Do the exact same feature that we did before. And well, we end up at this really big long number of like 263,169.2995. Raise that by the value of 72, divide that then by 64, and you get basically infinity on most calculators. And so we are then rounding, or we're rounding down and truncating our end result, which we get about 1. So if you go to infinity, you end up at 1. If you have a number lower or below 0, like a small minute number, ends up at 0. And then if you get anywhere near a real number, it ends up just being that real number, including 1, 4, 2, 3, 4, 5, 6. Don't matter. So there is a way to actually do the presentation we were just doing and click on them to actually get a sum result of like 2, 5, 8, 10, 15, 28, 32. And all that means, all that number represents is how, like, if you pick real close to yourself, each one of your numbers are picked real close to each other, you end up with closer to a real number. If you pick further away from each other, you'll end up closer to infinity or closer to 0. And either way of that, this kind of helps show that just adding entropy, which we're using the loop order to show, makes a huge difference. Basically, like, if we was to do all these again, but instead of the 2 plus 0, we just had the 2, or just the 3 instead of 3 plus 1, or just the 1 instead of 1 plus 3, or just the 4 instead of 4 plus 4, on those equations over there on the side, to represent the box number itself, none of this would really work. I mean, it all works exactly the same, truly, but you get less like towards infinity, not towards infinity. It's much harder to make determinations of what is actually going on. The more entropy we add here, or the more times we add in our actions, our loop order, different things like that, we can then get a much more on-off way to view things. For example, the closer we are to ourselves, the more to a real number we will get. Knowing if you end up with a real number as your weight, we know that exactly what you did. You're either on the exact same line or pretty much on the same line. If you end up at 0, but it's not 0, it's because it's way past 0, then we know you were nowhere near each other. Or if you're at 1 because it's technically infinity, then we know you're nowhere near each other. But anywhere in between, then we know we can make determinations of what you did. And the entropy, adding in the entropy, adding in this extra layer, not only does it like allow us to make more predeterminable information, but it also makes it less predeterminable of exactly what. It does hide more of what you're doing, which is the perfect point of the entropy. So just adding a second row. So when you reveal your name, you reveal one of those 2 rows, either one. It doubles the possibility of points your name may land on. And even though we didn't change the font size or how big the grid is, there are still issues, but just about all trustless sharing procedures will have those same issues. And to be honest, the more people you have involved, the less those problems actually are. Because again, that presentation I'll show you, we're done with 1 to work. Like, let me just do that. DTS. We're just going to put 1. So this works even with 1. Hooray! I got myself. Aha! Let me show you this again. 99. Okay, mine just works. Yeah, I don't have a computer good enough to do 99 parties. Alright, anyways, I hope that gets my point. There's a lot to do with entropy in this equation. So, hold on a second. I want to just... So, hey, if anybody out there can get this to Matt Parker, please do. I'd love for him to have a better version. That way, next year he can have a better... Try the version 2 version. But when it, like, you notice how I look at the fence and the grid numbers are sitting on in order to make and then use math in order to determine if something was good or not. And similar, how they were using maths to make causations or reasoning why they needed to do specific things. We completely looked at these in 2 different ways. They were looking at a traditional math setup, how you would do your proofs and all that. And I am simply looking at probability of possibility, and huge different way to do it. So when you look at trying to increase the probable chances that your numbers will lay on the same line, it makes more sense this way. And when you're trying to prevent someone from hacking the system, that's really the only thing you're trying to do. Prevent someone from being able to pick what line they are on for the left end result. Hopefully you guys got that. Now let's just go on to the next one. You already kind of saw. Let's get into it. Yeah. Right. So pins my nose. Okay. Let's find out what these omnios really are.
Of 5 squares. So, for example, this is one of them, made up of 5 squares. We would also have this one. We can also have this one here. 1, 2, 3, 4, 5. Oh, a little snake-like one here. 1, 2, 3, 4, 5. And in total, there are...
Okay. So that's what these are. These omnias are blocks lines to represent shape, pattern, and some other stuff. Cool. Let me give you that score one more time. Alright, so I want to show you the traditional way to build these. How is it not set on my marker? Sorry, for some reason I don't think it was on where I think it might have been playing in the background. Yeah, so
this is one way of generating them. Another way of generating them, you start with a square and then you number clockwise 1, 2, 3, 4. And then we're going to pick one of these numbers, say 2, add a square here. And then we continue the numbering clockwise, 5, 6, 7. And now we pick a new number. And the only rule is the numbers you pick have to keep increasing. So we couldn't now pick 1, but we could pick 4, for example. So pick 4, and then this becomes 8, 9, 10. Then I might pick 7, say, and if I pick 7, I can't then pick 5 and 6. Got 11, 12, 13, and so on. And
okay, that seems like a reasonable method. Now, if you didn't catch that, the actual first method is like you start with 1 and then you just bear it on to the sides, and that's about it. You just keep going, keep going, keep going. Cool. So I find these two original ways of doing this pretty much pointless. Yeah, so the only real rule is once you pick a number, you cannot go lower than that number, which we can also say when contains an infinite growing non-equilateral fenced grid. If you go in a direction, you cannot go back unless you are gapped away from the rest of the line box. The reason I say we can change the rule to this is because we are making this box line shapes. We are unhappy with the move. Well, we can simply remove the last block and go on, or we could even just rotate the set of numbers in a previous block as long as the end result still is acceptable. Let me show you what I mean by this, because this is basically like me saying I hacked their growth method to ensure you could find the most or best way to play this probable game each and every time. And then I'm going to show you a completely different way to do this. Okay, let's go. So here is a grid. I'm using the grid to kind of, because that's my way of doing it, is we're doing this on a grid fence, or a data line fence. As I said earlier, fenced grid. And here we're building one of the Omnios. So, pretty simple. I'm doing it their simple way. I got first box, I put it down, I put 1, 2, 3, 4 around it, I pick 3, and I then now can put 5, 6, 7 around it, I pick box 5, I go 8, 9, 10. Right now, I currently have 3 moves I can do. I can go to 9, I can go down to 10, or I can go down to 6. I can't go up to 8 because it would run into 2. And I could technically go to 7, but I can't go to 4 or 1 because I picked 5. So the numbers inside the box represents the number you've taken. You can't go back, you can't go lesser than that. So I kind of want to oh wait, I just realized a local file. There ain't nowhere to view this online except for right here. So excuse me for not having keywords for these. Alright, so here's an example of just rotating. After I've already put 3 blocks down, I'm going to rotate the numbers in that first block. Let's go back and show you what they look like before. 1 at the top, 3 at the bottom, 4 and 2 and 3 was taken. Now I'm going to rotate them twice, clockwise. 1 is taken, 3 at the top, 2 on the left, 4 on the right. And it still works. Still perfectly okay. There's nothing wrong here. I'm just trying to show you that like we can still do these things and not break the system. So here is the box. As you can see, this is after the rotation. We've rotated it twice, and now we're continuing on. So we have taken box 1, and then we have taken box 5, and we have taken box 10. Now we have 3 moves we can make. I keep forgetting this. I need to move my chair a little bit. So we have 3 moves that we can make. 2 moves we can make. I mean, we can go 13 or 12. Okay, that's what's up, right? You can go to one of those spots. Okay, nice. What? What if we rotate this very bottom box that we just did? Well, we rotated it twice clockwise, and guess what? We got no extra moves. So if we look here, we're still in this setup. We're going to go one more step, trick box 11. I now have 3 possible options. I can go 15, 12, or 14. Okay. Keep in mind, I already have 1, 2, 3, 4. I already have a pink note. Right? So, what happened if I had never rotated this box that's now behind my head? So I'm going to show you what that looks like. First off, here's what that would have looked like. We would have taken the 10, and we never rotated clockwise, so then we had taken 13 instead of 11. Well, guess what? I now only have 2 available maneuvers. 1 less move this time. So simply, at any point in time, I can always go back and rotate these blocks to potentially open more maneuvers. Now, I'm aware you're probably going, but your rules won't work for compacted objects. Oh, no, I got you, bro. I got you. So we're going to build a compacted object. So, started with the very first spot. Somewhere in here. Yeah, here we go. Very first spot. 1, 2, 3, 4. Took the 1. We now have 3 spots open to us. 2, 5, and 6. We can move. So we're going to take 2. And now we have 8, 9, 10. Now we have 4 maneuvers we can do. We can go 6, 5, 8, or 9. Which 5, 8 are 2 different moves. Doesn't matter. Basically the same. And there it is. Here's a box. Compacted box. And we have 3 moves we can do. 11, 12, or 9. Obviously, I can't take the 6 because I took the 8 as well when I took the 5. And that's fine. Because the reason why we can do this is because we did an offshoot. So when we were going right, we started going in one direction, going to the right, and then we chose to basically step back and offshoot. And I like to call this as a test. I want to test if I want to go that direction or not. I decided I didn't want to go that direction. So I went back to the way I was going. Except instead of flowing back and through, we just continue in 2. Because I can. Now, what if you can't? Here's an offshoot where you can't just go back. So, in this case, we started down here and we're moving to the right. And we have 1, 2, 3, 4. We take the 1. We have 5, 6, 7, 8. So since 1 is the leading block, I test waters on 5. I go up 1 with 5. And I realize, you know what? I don't want to go up that way anymore. So I go return to 1 and move forward on 6. Kind of like how we did before where we made the square. I started one spot, moved, didn't like it, went back to where I was before, and went a completely different direction. And it's not the opposite, but it is different. And because of that, now we have an offshoot. I continue going. I can now go multiple different directions now. I can go up to through 9, or I can take the 10, 11 block, or I can take the 12, the 13, or the 7. Because I have not taken anything, and the lowest number I've taken is a 6. I have literally set this up to be the best presentation with those numbers. In case you were wondering. Because I could have done this in a method where, you know what, I wouldn't be able to go through 7, and I wouldn't be able to go through 13. Or, I mean, I could go through 13. There is a way to do this where you couldn't, 7 would be a lower number, and we would have taken the 7, so that could have been a 5 or a 6, and so I wouldn't have been able to go down that way. And basically what this means is, like, now we have 2 offshoots. I can pick either 5 offshoot or 6 offshoot to continue. Because they're both offshoot off the same node. 1 block node. I do have a little bit better explanation of that. Let me see if it's in my notes. So, this is a common offshoot. We started similar to 1, and then have the opposite rotation for the sum placement. But then after that, we go into the same. So the only thing here different I did is when I placed the first one, instead of putting my numbers on there counterclockwise, I went clockwise. Oh no, instead of going clockwise, I went counterclockwise. And then the rest of the times I went clockwise. And that gave me the number one best maneuvers, all the maneuvers I wanted to go. I just start with that one in the direction I want to head towards, and I'm good to go. When we got to like 5, we decided we didn't want to continue that offshoot. We went back, continued on the block line. So as you can see, this shape has many options, and more so compared to others if we rotate the sums of the blocks. It can be very dramatically reduce the number of moves. So here is the same exact one, simply rotated, I think all of the blocks but the first one. I think I rotated, no, right? Yeah, I rotated all the blocks but the first one. And as you see here, we now only have 1, 2, 3, 5, 6. Technically, we only have 1, 2, 3, 4 moves. We only have 4 moves, but it's 1, 2, 3, 4, 5. Technically, really only 4. And this shows that just rotating one block can make a huge difference. Rotating all the blocks can also make the same exact difference, whether it's minimal or max. And so I kind of want to show you something else. Because basically, me go right back real fast. Basically, here, this simple shape, I simply just rotated the box. Boom. And we got something hugely different. So, what happens when we have a shape made? Well, we can't rotate those boxes anymore. You know what I mean? That doesn't make any difference now. But we can still do something, right? So this is where I basically first started. I was looking at the different shapes and trying to find more. This is how I got started into this problem, to be dead honest with you. And which is where I came to my conclusion, where I came up with my rule set, and where I am coming from. Here's a very basic Intimo. 1, 2, 3, 4, 1, 3, 4, 5 blocks. Now we can push some of these blocks to form new pentanotes. Here I pushed the block that was right behind my head and pushed it up to the right, and now I made the opposite side, the opposite of what we just had. Like we had this. Now we got this. It's just been rotated on its head. I had one move to make that. Okay. Well, what if I had moved the other block down instead? Well, I would have made an L, a completely different shape. I just took that one was on the 2 side. So basically, what was the graph? So to get rid of the graph, So basically, 0, 1, 2. So it'd be box number 2, 3. 2 plus 3 is the box I'm talking about. 2-3 was moved to 4-2. Make a brand new shape. Now, but we can actually make more and more of these shapes like this. It's a different way to look at it, different way to do this. Here we go, brand new shape. Pushing finds many more forms, but you have to have your set length. So you have to have a shape with a set number that you like before you can start pushing. So we need to have all the lengths before we push. So in this example, can we push left or right? Well, if we try to push left, we're going to run back into the main line. We can't do that. That's one of the rules. Never run back into the main line. Kind of like you're playing Snake. But if we had pushed right, well, we just made a brand new shape. And we're not running to the main line. We have empty space, nothing. No problems seen here. That's great, right? Absolutely. So, okay. So we can push right to the empty space. Basically, pushing is similar. Pushing is basically just rotating that base block. So, for example, that block right there at 4 plus 3, I'm then have the lines going off to different question marks. That block right there is not the base block. That's the block that we're going to affect by rotating 3, the block right above it. We can rotate it clockwise or counterclockwise. So, basically using these rules, using the way we're doing this, for as long as the pushing is rotating that base block, but we can also say like pushing is moving to a different face of the same block without skipping over any blocks or faces. And this works on a 2D plane. This also works eventually on a 3D and 4D plane or any higher plane because they all have faces. They all can form some form of block and multi-forms of blocks and different ways to look at those blocks. So you could have a block within a block within a block and have all those blocks move independently, simultaneously, or in conjunction with each other. And this might be a different way to find basically three-dimensional maps, even on a 2D plane. So here's the rules. Generating omnios. You can see it's still a little bit different, but generating them specifically over data rail fences. So the starting position determines your null. You can only move to a higher position. Basically, you can only move away from where you started. Now, doing an offshoot towards the start position isn't exactly the same thing. We mean the main line has to move away from the start. If you're moving plus or minus on the x-axis and you hit a wall, you must overflow. So if you're moving to the right, so you're going upward, or if you're adding upward, going upward in the number scale, on the x-axis, you hit the edge, you have to go southward on the map. I just realized those are flipped. Sorry, dyslexia. If you're going right, you must go down. If you're going left, you must go up. Those are flipped for some reason because I'm dyslexic. My bad. So if you're going right or going positive on the x-axis, you must go downward or southward on the graph. And if you're going right or you're subtracting on the x-axis, you must go upward, northward on the graph. Sorry, those are flipped backwards. You cannot touch another block. You cannot touch the main block line. You cannot touch another block line of the main block line. Offshoots are allowed if they are before the main block line. So we can use it for testing. So pushing can be done after a block line of a certain length is found in full length. So after you have found a set of length, and you say like, all right, this is the final length, you start pushing. Can't push before that. And that's kind of important. So the blocks are kind of permanent until you're done with your length, and then you can start moving them. Alright, so I have another chart to help make this make sense, hopefully. So this orange bit is moves we can do once we have a shape with a full length. So these are moves that we can do after it's done. So these are the pushes. Now I got two different pushes here. I got one going up to the right and one down to the left. You notice neither one of these are going towards the 0. None of them go from the start. And I even showed all the moves that we did to get to where we are. So this purple thing is the offshoot move, which can be abused to offshoot to an offshoot from an offshoot, to then return to the main line from that offshoot or that offshoot to form compact block shapes in this place. We see we start at 0, We moved up to a shoot. We did an offshoot. Was not happy. We turned back and did another offshoot, and then continued on from there. Everything in the green are basic maneuvers. So a move goes to the right, a walk goes to the left, a crawl goes down, and a climb goes up. You have a way to make sense of what you're doing, and cool. The only extra note is you cannot push into a box shape. Alright, so I think a good way to look at these omnios is that we are really talking about complexities here. And for example, this is a small fun project I'm working on. I'm going to show you here in a second. Let me get to it. This is again a local file. I do not have anything available for this online yet. But this is a fun little project I'm working on to attempt to find as many of those omnios as possible and as fast as possible, starting with user choice and then extrapolating from there. But at the moment, it actually does all the work for itself. I just slowed it down with this nice little button so we can actually see it in steps. So if we ask, instead of how they word it and how they whatever, if we ask what complexity mappings are possible from complexity connecting nodes at specific node lengths. Well, that is like these omnios can be viewed as each box is on. Let me say that again. We can view this as each node box is on when we see it and connected by one serial cord to another, daisy chained together. The only way you can triple task one node or quadruple task one node is if the extra cord is only connected to one. It's only connected to one other node, so that node has no other connections after that, and is before the line continues past it. Once we are all hooked up, though, we have the link. We can move nodes around. There are phase connectors on each side, for as long as we can have a possible communication from the start to the end uninterrupted. So I can go from the start to the end, even with those offshoots there, without being interrupted. Using these new rules with even the old and trying the push method before fixed or free determinations, we should be able to find more unique patterns, then extrapolate from there to find the free, flip, reverse, and manipulated versions of the exact same shape. It should make this faster and easier, so to speak. Now let's get into the example. This is a very crude one because it's one I'm still working on. So here's the graph adder. So there is a way to actually give all graphs an indexable range on two different directions. So if you add down into each row, you end up with 4 boxes. And then you go to the right, you multiply, you can drop those 4 down to 1. Or if you start just going to the right, you multiply and then add down. So either way it goes, you can have up to 5 numbers for both columns and rows to represent them. So we have the guessers, we have columns, it's even checking the rows, and then we have basically an array, and basically the array is really how we're actually defining everything. This little one that you see at the very top, that's the very first move we made. That is that's a null grid. It basically sits in the center. It's like a center box in the middle of the actual grid that has a pole extending out through the grid that allows things to align. So it's being used as an alignment row. And so I'm just going to click do this. So, and I just did that, and it basically keyed a corner. Now we know which way is up. And now it's going to find a shape. So each one of these numbers that's being put in is the actual step that we're on. It's the loop count. Okay, we have found our first shape. 1, 2, 3, 4, 5, 6, 7. I forgot what that was called. Polygon or whatever. Yeah, got one of these. And it is a very basic one. And a zigzag. It's like staircase going up. When we see our graph adder, it's 13, 15, 32, 15, over 225. And if we was to remove our key, then it's technically 13, 15, 32, 12 at 223. Our guessers, we can see they're not guessing it the same. Our row and column ended the same. We have mod check, dom check, row checks, pickers, and the pickers are literally the like placing locations where they're going to place stuff. So with this one, I believe we can go a little bit further before we start having errors. Try it. All right, it actually built more to the graph and decided to go down again. Now at the moment, you can pretty much guess it's going to keep doing the same thing until it finds an end, and then it will start doing something else. But you're going to see in 1 second, we start running into errors after that. So it does auto grow. It does, so the plane doesn't have to be set to a finite plane. It can be infinite growing plane. But when you're just trying to map the complexities within a gridded fence, it's a little bit easier to understand what's going on. And to be honest, I use this methodology with Supposix to do something else. So it's where my thing came from. Like I've been doing this with Supposix for years. And I came across this video and I was like, what? I couldn't believe my eyes. Like there's other people out there wondering about this stuff, and then you got some idiot like me actually mapping these things and finding mathematical formulas to actually help us make fast. Okay, fun, fine, well, fun so to speak. But let's get to the last point, probably the most important point, or probably if you're here, the reason why you're here. Talk about using YouTube videos in a new way. What is this here clip? Viewbot exploit preview by the Spiffing Brit. I am completely shocked. Completely and utterly
Forms of engagement
shocked.
with this video and the channel will work positively to this video's success. From commenting, liking, sharing, and even voting in community posts, weird things like making clips of this video are another brilliant way of adding views. And in fact, there's a weird exploit that you can use to view bot without damaging a video's performance. Anyway, no, I'll save that for another day. It's too complicated and potentially illegal. But yes, it's forms of engagement with complicated and potentially illegal. But yes.
Did he say complicated? No. Oh. He already explained basically everything. It's not really complicated. Okay, I'm sure he has a more complicated version. There's a simple way to do this. Now, I don't exactly have something to show you for this one, so give me a second. Give me a second, okay? What exactly does this mean? Well, we can clip sections of videos that are not doing so well, like the ad reel sections or the promotion spots, places people tend to skip. Then we can use those clips, kind of like as embedded media on your website, and to make ads. This will keep your ad under 1 minute, ensuring that you know it's not too long. It won't get too terrible ad. And it also ensures you know what the ad is. You can kind of guarantee your ads. And so now keep in mind, I am let me just say it. Let me say it. You make a video, you have a couple of ad spots, some in the beginning, some in the end, maybe one in the middle, that you choose to put in. Maybe you got a sponsor to say, hey, if you get enough views, or if you can prove that that spot in the video has more views, you have a potential chance of getting paid. So you then make clips of these 3 ad reels or whatever, and you're going to then find a way to embed them into your website. When people show up, they pop up, or perhaps they're just there playing one at a time. So when people watch these clips, because they're official YouTube clips, like the one that's actually on screen, an official YouTube clip, I'm on the site, so even if I'm not on the site, the video is from the site, so the views will go towards it and stuff like that. It's technically going to this British Spiffing Brit because it's a video and such. But you get to this point where basically those are normally spots where you get the worst views, you get the lowest metrics for that part of the video, and you can basically inflate that a little bit more off the record, so to speak. But it gets a little bit more convoluted than that, because you can do this with more than just clips. You can do this with any embeddable video that is monetized from any site. YouTube would just be probably the easiest one to explain it, because YouTube works like Spiffing Brit explains in that video. As you go back and watch his video, he basically explains that anywhere you watch a YouTube video, for as long as it's coming from YouTube, it counts towards the video's retention and all that. It just averages out, and instead of being directly influenced. So as long as you have something there that is there, you have some views, some watch time, it will only increase it by making it better. And at the same time, you have a chance that you don't really have views, but trying to make it worse by not having views there first. So if you're trying to use this, you say, in a view bot type of method, and you're not getting actual views on top of it, it will actually hurt you helping you. And so, now keep in mind, I'm not saying these clips are even embeddable. I'm just saying finding a way to use them as embeddables would allow you to have this clip-based ad system. And not only does this direct back to your YouTube videos for that sweet views and such, but if you are monetized to YouTube and then you send your clips over another monetized platform like Twitter, then you can actually get double the return for the same video. Think about it like this: like, if you don't have a website, or you do have a site, you can still do this. You can basically push your clips to your Twitter or Facebook or Blue Sky or Mastodon, and if you're monetized there, you'll get double the return, once for them interacting with your post and another for directing back to YouTube. Now, I'm not saying you can do the embedding video postings on places like Twitter and Mastodon, but I will point out that Twitter does have a method for pulling videos and self-embedding them if they're able to through the link. So you can literally get views on Twitter and YouTube simultaneously without the viewer actually going to YouTube and leaving Twitter. So find ways to embed these links that will allow you to do this. Is kind of the golden goose. Find that golden goose to lay those eggs. Now, if you can't get this clip ads method working, you have all. Or I said that wrong. If you do get these clip ads method working, you have a whole new side of your content creation business you probably didn't even think you could really do, which is basically providing ad hosting for your own platform or a views platform. So, like when you go in over Twitter and stuff. And keep in mind, there's a chance Twitter videos embedded on other sites help you. Chance. Today, I wanted to go over some things in my personal life. Yeah, because it's numbers, man. I mean, as a number enjoyer and a I-doer, I hope you all found today's episode to be a bit different. And if anything, perhaps you just need to take your perspective and turn it on in and see another methodology that works for you to get to the same place. For example, the sharing ideal, I mostly just added entropy, one extra mixing layer, which Matt figured out before I. But I also added a verification pass, so you just pass it again after everybody's done to make sure someone didn't really screw everybody else over or something like that. But well, they didn't really do much, right? But that made a huge difference in the output, because adding a second layer of a picking for reveals basically gives almost double the points of possible outcomes without adding anyone else to the equation. This extra reveal row shows that can be expanded on, but also, to be honest, from the maths, the number of participants is the more important. So 3 rows, 4 rows doesn't really make a huge difference as long as you have at least 2 to pick from, and then your main secret row. Basically the more participants with these 3 rows setup that I'm doing, it gives you a greater distribution of weight across the players based on their actions for the grid size used. Then I jumped over to the number 5 video, and I showcased the Omnios and how they are traditionally found. And then I showed my version, which is just a math trick that I actually use when I'm playing with myself, when I'm playing like dominoes or triangles, or as sometimes called puzzles. And I looked and looked and looked everywhere for these. Okay, my grandma had these. Each one of these puzzle pieces is a like perfect triangle, right? Or an isosceles triangle. Some kind of, they all exact same triangle. And I do believe like they're not quite 90 degrees. I think they're slightly less than that. I don't know. Anyways, they would have pictures of partial pictures, and when you put them together in a very specific way, it would make a picture. So my grandma had one of cats and dogs and one of skiers. So when you put the cats and dogs together just perfectly, all the cats and all the dogs would be whole. It would be whole animals. And when you did the skiers, you do it two ways. One way, you'd have all the skiers with one skier behind, like, I think it was a snowman. And if you did it the other way, perfect way, all the skiers would be revealed, and the snowman would then be in two pieces. So, how did I do what I'm doing now? What about these 5 puzzles with my grandma's, from my grandma, way back when, from like the 70s? Well, it has to do with this right here. So here we have 4 triangles. So here's one of the triangles. So 3 triangles look exactly the same. They're exactly this exact same triangle. The ones on the corners are this exact same triangle. And they're placed in the exact same way. But the one in the middle is upside down and is not the same. And I say that it's actually exactly the same. Exactly the same as the others. They're all exactly the same. But when you put them together in this very specific manner, you end up with a cube inside of a triangular housing. Like, you can actually tell there are now walls behind that cube and a floor that cube is sitting on. That cube is inside of a room that we cannot see. We'll only see part of it. Insane. That's kind of how my method works. You have these little subgroups within main groups that when we rotate and arrange them a specific way, we get different types of outputs. For example, we can actually rotate these to rotate the box in almost the exact same manner that we were rotating to get those omnios. So finally, I then ended with a real doozy. And I know you guys probably, it was the fastest doozy you ever seen, but it's the quickest and easiest way to look at it. Using your own created content to make ads for your own platforms and websites utilizing YouTube clips or X clips, because the clip still counts to watching that section of the video. So if your ad views get the least views, you can pump it up and at least get your video back on the algorithm while giving yourself ads on other platforms that directly help you in one or more ways. So all of the images from the Omnios will eventually be available on GitHub when I put up the Omnio repo in a couple weeks. The generic trustless sharing protocol is already up on the GitHub, and we did show that preview earlier, so go back to that QR to find it online. And we'll basically, I hope you all enjoy your New Year's and holiday and have a great start into Christmas year. Bye. What the heck is wrong? Something happened with my Video's not gonna work right. Sorry. Nope, heck no, I'm gonna actually try it one more time.